Now, it's time to analyze linear search algorithm. Any algorithm can be analyzed in terms of its best, worst, and average case performance. Let's begin our analysis of linear search by discussing the best case scenario first. Here, the best case occurs when the target value is the leftmost item in the array. This is because the algorithm starts searching of the item from the leftmost part, so searching for leftmost item will give us an advantage to achieve the best case time complexity. For instance, in the array given below, if you are searching for the target item 4, the algorithm starts at the first element. That means it checks list at index 0 equal to key, which is 4 equal to 4. Since this condition is true, the algorithm immediately finds the target element. In this case, the search completes in just one step, resulting in a single scan on memory, leading to a time complexity of constant which is represented as T of n equal to big O of 1. This indicates that the time taken is constant regardless of the size of array. Now, let's go through an example of linear search algorithm to illustrate the worst case scenario. In this case, our target value is 7, which is located at the end of the array. We are using the same example. Here, the algorithm begins by checking the first element, that means list at index 0 equal to key. This translates to 4 equal to 7. The condition is false, so we move to the next element. Next, it checks list at index 1 equal to key. This is 2 equal to 7. Again, this condition is false. Then it checks list at index 2 equal to key. This is 23 equal to 7. Still, this is also false. Next, it checks list at index 3 equal to key. This is 8 equal to 7. The condition is still false. Now, it checks list at index 4 equal to key. This means 6 equal to 7. Once again, the condition is false. Finally, it checks list at index 5 equal to key. This is 7 equal to 7. This time, the condition holds true. The target is found. Here, in the worst case, we have done the maximum number of comparison in a list. In the worst case scenario, the algorithm had to check all 6 elements in the array before finding the target at the last index. Since the algorithm had to scan through every single element, the time complexity in the worst case is expressed as T of n equal to big O of n, which is linear time. This indicates that the time taken increases linearly with the number of elements in the array. Finally, let's analyze the average time complexity of this searching algorithm. In the upper array, searching for the second, third, fourth, and fifth item will have a probability to achieve the average time complexity. To compute the average case, we consider the target could be located at any position in the array. For any size of n, the average position of target will be approximately in the middle. Therefore, on average, the algorithm will make about n over 2 comparisons. Thus, average case time complexity is expressed as T of n equal to big O of n. This means that while the average number of comparisons is n over 2, we simplify it to linear time complexity for larger n, because in n over 2, the degree of polynomial is 1. Finally, we have thoroughly analyzed the linear search algorithm in terms of its performance across different scenarios. In the best case, we experience a swift search when targeting the leftmost element, resulting in a constant time complexity. Conversely, the worst case emerges when we search for the last element or an element not present in the list, which requires linear time and equivalent with the size of an array. The average case occurs when the target could be located at any position within the array, leading to approximately n over 2 comparisons, still yielding linear time complexity. Moreover, it's important to note that the space complexity of linear search is constant, as it only requires a fixed amount of additional space regardless of the input size. To summarize, while linear search is straightforward and easy to implement, understanding its performance characteristics is crucial for selecting the right algorithm for our needs. Thank you for your attention.